Welcome to SolidCAM Professor. I'm Sydney, your SolidCAM Professor, and in this session we'll be doing a demonstration of high-speed machining, HSM. SolidCAM HSM is a very powerful market-proven advanced 3D mill and high-speed machining module for 3D parts, aerospace parts, and molds, tools, and dies. The HSM module offers unique machining and link strategies for generating advanced 3D mill and high-speed toolpaths. In this part that we have on our screen, I'd like to demonstrate our roughing options and some of our constant Z options. Now, what I'd like to do is actually go into this deep pocket while using a tool that's only sticking out a short distance from the holder itself. And we all know what the problem with that is that the holder itself a lot of times cannot go in because it'll crash into the walls. I'll start my HSM operation, and I'll choose from my list of operations contour roughing. You'll note that my target is here automatically. That's my geometry. That's because I've defined my target already in my CAM part tree. Therefore, the target is automatically put in there. Now, the tool that I will be using, as I said, will be a 30 millimeter end mill, but the distance that is sticking out of the holder, it's only 20 millimeters. As you see over here, this tool is a very short tool. My constraint boundaries in this particular case were created manually, and that is actually a simple chain that was created around the top of the part itself. Now, in my passes area, since I'm doing a rough cut, I'll leave 0.5 millimeters off the edge of the part, off the surface itself. And you'll note the moment I did wall offset of 0.5, my floor offset is also now at 0.5 millimeters. Now, since this is a nice big tool, I'm going to take a down step of every 10 millimeters. It should also be noted that in HSM, a lot of these fields are connected one to another. So if I make a change, for instance, in this field here back to 0, you note also that my tolerance automatically changes. In other words, saving me the time that I do not have to go and change my tolerances or worry about them at all. I'll go back to my wall offset and change it back to 0.5 as said before. And if I'm not sure what any of these fields do, I can simply also right click on any field, go to view parameter information, and you'll see I have this parameter information, what's ever written over there. Plus, if I click on the arrows on the side, it gives me a complete explanation of what that field does. It can be this field or any field I choose. I'll have the same effect. Let's continue on down now to our link area. In our link area, we have our climb milling and we have our ramping. In this particular case, I want to helix into a part and using a ramp angle of 10 degrees. Let's do now a simple save and calculate. And in our simulation, using our solid verify, we'll see that our tool will start machining into the part itself. Now, as it goes further down, and I'll stop it the moment it gets to a specific point, such as right now, and we'll take the side view, you'll note that my holder is actually inside the part itself. What's actually happening is actually working its way down, but avoiding from the holder from actually crashing into the part as shown over here. And this completes as far down as it can go. Now, the control for that is actually in my tool area. If you'll note, in my tool area, we have an additional option here called holder clearance, which actually controls the distance to keep away the holder from the material itself. Now, in my next operation, I still have to deal with these areas over here, these large steps that I have over here, before I actually start my finish cut. So for that, we have an operation in HSM called rest roughing. If I were to open up my HSM, you'll see we have the operation here, the option called rest roughing. The rest roughing will only work on those areas where the previous HSM operation did not clear off. Now the tool obviously that I'll be using this time has to be a tool that is longer. This way it can go all the way down into the part, clearing those areas as well. Now my constraint boundaries will stay the same. Now we have an additional option here called previous operations. This shows the previous operations that were done in HSM. In this particular case, we only have one previous operation. Therefore, that's all we see over here. Now, in my passes area, again, I'll have this at 0.5 millimeters. And my step down this time, I'll have it at every 5 millimeters. Now, in my link area, I'll change my ramping from the helix that I had before to plunging, where I can go straight down, and I'll have my lead in go down with a radius of 5 millimeters. Now, when I go into Save and Calculate, we'll take a look at our simulation, and I'll run my simulation. You'll see that the tool now is cleaning only those areas that have to be worked on, cleaning away each step. And even now, when it gets to the very bottom, it will note that it even will pick up those extra pockets that the previous tool could not go into, as shown over here. Now, in my next operation, I want to now finish these walls over here, and I'll be using a constant Z option, but I will also be using a tool that can take big steps on these walls, and that tool will actually be a tapered tool. So I'll start my new operation of HSM in this part, and I'll use the option of constant Z for my list of operations. Now, the tool, like I said, that I will be using will be a tapered mill, where the angle of the tapered mill is the exact same angle as the wall of the part itself. Constraint boundaries stay the same. Now in my passes area, I will change my step down. Since I can take large steps because it's a taper tool, I'll change it to every 10 millimeters. And I want my Z bottom in this particular case only to go up until this step over here. Now, in my link area, we have our leads as we're going into the part. Now, the lead is actually going in at a specific angle, but I'm just to change this angle now to 80 degrees and do Save and Calculate. Now, when we take a look at our simulation, and again, we use the solid verify simulation to show the part, you'll see that the tool is going in, and I'll stop it at this point. And as I turn the part around, you'll see that as it finished its first level, it went down gradually to the next level, completing that step until it gets to the next level, and then continues down exactly until it reaches the very bottom of the part. Now let me just take one more step over here and show this in the host CAD, and we'll take actually a look at our tool pass itself. You'll see that the tool pass is going around, and every single time it completes one level, it's actually going down now gradually until the next level, and then continuing on, and the same thing as it goes all the way down. In this next part, I'd like to demonstrate some of our finishing options that we have in HSM. Now, what's special about this part is the fact that I'll be using in the beginning a large ball end mill, an 8 millimeter end mill, ball end mill, whereas these radiuses over here are only 3 millimeter radiuses. In other words, the actual radius of the tool is bigger than the radius over here, and we would like to actually go in a smooth cut up these walls as shown over here. In addition, we have these areas around over here, such as these holes and these slots, where I'd like to have the tool go directly over them as it machines the part. Now, I'll demonstrate this by using the option of finishing in linear machining in HSM. And I'll open up my operation and use the option of linear machining as shown here. The tool that I will be using, as I've mentioned before, will be an 8mm ball end mill. Now, what I'd like to do though is I'd actually like to create a fillet over here that's bigger than the fillet that we have here, so that the tool can actually ride up on that fillet rather than go into a sharp corner in that fillet itself. So what we have here in HSM is we have an option here called Apply Fillet in our geometry area. If I were to use that option, I can simply go in and define a tool that's bigger than the radius over here, and also bigger than the tool that I will be using. Say I'll define a tool that's a 10mm with a 5mm radius on the corner, and calculate that. Now, if we show what actually happened just now, is you'll see that the program automatically found every single one of those corners and created a virtual bigger radius on that corner itself that would allow the tool to actually ride up on those corners. I'll simply accept that. Now, in my constraint boundaries, I'd like to create my boundaries automatically. But my boundaries, when I create them automatically, must include boundaries going around these areas as well as just the outside shape. So we use the option of Auto Create Silhouette. If I were to do that, what will happen actually, as shown over here, you can see that there are boundaries created exactly according to the outside shape of the part itself, as well as the holes and slots that are in the part itself. Now, in my passes area, I'll make my step over every 2mm, and in my link area, I would like to have this actually go directly over back and forth. So I'll have, first of all, a simple ordering to have it go simply back and forth. But to go directly from one area to the next, I'll simply have, in my strategy area, stay on surface within. That means if the area over here is bigger than this value over here, it'll jump up. However, if this area is smaller than this area over here, it'll go directly to the next surface, and I'll write over here 40mm. Now, if I do save and calculate, and then simulate the part, you'll see that my tool will be going directly over these areas over here as shown. And if I zoom in to this corner over here, you'll note that my tool path is now working exactly along that virtual radius that I created along the part. So instead of having a sharp corner over here, I have a radius turn on the part, making for a smoother cut on the part itself. Now you'll note that these walls over here, this surface finish is not necessarily the best using the linear option going across. So there are two ways we can deal with that. One way, within the linear option, we have in our passes area something called cross finish. If I were to activate my cross finish and say do a cross finish after, the program will automatically recognize those areas which are steeper and do a cross finish on those areas. If we take a look at our simulation, you'll note that when it finishes going across the part as done before, it'll come back and work on these areas in a cross finish manner as shown over here, covering every single one of those areas on the part. Now, another option we have is I can use a different type of operation as well. We know that constant Z works very well on these type of steep areas, where linear works really nicely on the flatter areas. So what we'll do is as follows. We have here an option called Combine Constant Z with Linear, where I can do in one operation both linear and constant Z. I'll use the exact same tool I used before. My constraint boundaries will stay the same. In my constant Z passes, I'll have a step over of, say, every 2mm, and I'll limit my angle of operation to work only on areas between 40 and 90 degrees. In my link area, I'll just change it now for bidirectional. And now when I go to my linear passes, you'll note that my angle limitation is automatically now between 0 and 43 degrees, giving a 3-degree overlap between the two operations of constant Z and linear. Over here also I'll have a step over of every 2 millimeters, and in my link I'll leave it at bidirectional. Now I'll do save and calculate and then simulate the part. And in my simulation, you'll note that it works first on the constant Z, on the walls themselves, and then it'll work on the linear operations on the flatter areas, giving a really nice finish for the flatter areas, covering every single aspect of the part itself. Now, there's still one more thing we have to deal with. These corners still have to be finished in any case using a smaller end mill. To do that, I'll start a new operation of HSM, and we have here an option called rest machining. Now what the rest machining will do is as follows. It will actually automatically pick up those radiuses that were bigger and work only in those areas using a smaller tool. The tool that I will be using will be a 3 millimeter ball end mill. My reference tool is the tool that I will actually be telling it at what distance it'll actually start working for the rest material based on the tool that I write in over here. Now, before I made a virtual radius, created a fillet of 5 millimeter radius, so I'll use a 10.5 millimeter diameter tool, causing it to have a little bit of an overlap of 5.25 for the area that it has to work in. Now in my passes area, I'll have my step down and step over at say 0.2 millimeters. Let's take a look at the results. If we take a look at our simulation, you'll see now that the tool path is working exactly on those areas around the entire part, not missing any one of those corners, giving for a really nice smooth finish. Now if I zoom into an area like this, you'll see it even does a really nice overlap between the tool passes, causing a really smooth finish, exactly the way it should be done. In this next part, I'd like to demonstrate how we can actually work within this area, and I'd like to do two things. I'd like to show how we can just have the tools automatically pick up these borders and make a tool pass on those meeting points between the wall and floor over here, and basically every single one of those areas. And then I'd like to show exactly how we can actually work in those areas, having the shape of what those borders have actually created. I'll start my operation of HSM, and first I'll show the option of pencil milling. When I do pencil milling, I'll choose a tool, say a 4 millimeter ball end mill, and I'd like to actually just to have a tool pass go on every single one of those areas. First of all, I'm going to create a border area manually, only working in this area over here. We have the option now of passes. In my passes, we have our bitangency angle. As shown in this picture over here, my bitangency angle will automatically pick up a border wherever that tool will meet a floor and wall of anything above the degree that's written over here, and I'll put in 15 degrees over here. But since my tool is actually smaller than this radius, or actually the same size as some of the radiuses, those areas it will not find that kind of an angle. So for that, I can just simply build an over thickness of the tool, say 5 millimeter over thickness of the tool itself. Now when I do save and calculate, and then simulate, you'll see that in my simulation there's a tool path being created on every single one of those areas, whether it be over here on these walls, on this wall in here, or around here. Every single one of those walls has had a tool pass done around it with this option. Now what I'd like to do now is I'd actually like to have these areas actually machined, cleaned, but according to the shape of each boundary that was machined. So if this area is a round boundary, I would like to have this area done in a round shape. If this area is more of a boxy shape, I like to have that done as well according to that shape over there. For that, I'll simply go into my operation and choose the option in HSM of 3D corner offset. 3D corner offset basically works step over in those areas by finding those pencil passes that I've created. Now, the boundary will stay the same as done before. In my pencil passes area, I'll use the same values as I did before for my bitangency angle and my over thickness. And in my passes, I just simply say how much do I want to have the tool path step over at each time. I'll do a simple save and calculate and then simulate the part. You'll see in the simulation that my tool path is being created according to the shape of each area. For instance, this area is taking actually the circular shape, and now when it gets to these other areas, now it's taking the shape of this area over here as well. The same thing around over here and around the part itself. Now when it gets to these areas, it takes the shape of those areas until it completes the part, and then when the part is completed, you'll see that every single area will have the shape of the area of the boundary that was created around that particular area. As you can see now, if I were to change this into my top view, you'll see that every single area has the shape of that area that had to be machined, giving for a really nice, clean, and aesthetic finish to your part. Now, in this part that we see on the screen is an actual mold that is for a computer mouse. Now, we've used all of the HSM operations over here to actually produce this mouse, and I'll go over some of the highlights to show exactly how this was done in the smoothest and best possible way. Now, in our first operation, we used the roughing operation to take out the bulk of the material from the outside using a 12 millimeter end mill with a 2 millimeter radius at the corner. And we left over about 0.3 millimeters on an offset on the wall and the floor. And we also told the program to detect core areas, in other words, to come from the outside into the part itself. If we just take a quick look at a tool path that we have created on the part itself, you'll see that's basically clearing every single area on the part itself, going back and forth until it cleans out the bulk of the area. And this is how the part looks at the end of the rough cut, as shown here also in the solid verify mode. Now, in our next two operations, we've done a rest rough on the part itself, cutting away those areas that still have to be cut away before finish cutting, using smaller tools. We used an 8 millimeter ball end mill, and leaving in our passes area wall offset of 0.2 millimeters, going down every half a millimeter. And in our next operation, we did basically the same thing, but instead this time we used an end mill that was a little smaller to even get further down into the part itself, using a 6 millimeter ball end mill on the same geometry. And in our passes area, again, we use 0.2 millimeters, going down every half a millimeter. But it should be noticed also in our previous operations, we have both of these operations checked off. In other words, basically looking at both of these operations to decide where it has rest material to take off. And this is how the part looks at the end of our rough cuts and our rest rough cuts. If I were to go into my next operation, my linear operation that I've done over here I've actually done a semi-finish. If we take a look in our passes, we'll see that we're actually leaving 0.07 millimeters for a finished cut itself, but we're using a linear fashion to machine this part. Also, if we take a look at our geometry, we've created fillets in the corner. This way, that small end mill that we'll be using when it gets to these corners will simply glide over the corners, not leaving any kind of marks on the part itself. The tool itself is a 6 millimeter ball end mill. If we take a look at our simulation of the part itself, we'll see that the tool is working across the entire part for semi-finish, leaving 0.07 millimeters on the part for the finished cut itself. And in these areas, these filleted areas, we can take a quick look in over here, and you'll see that these corners over here are not sharp, they're actually radiuses instead, giving for a nice smooth cut over the part itself. Now, in our next two operations, we've done a rest machining on the part itself to cut in those areas where that previous tool could not go into. But again, we'll also be doing a semi-finish on the part itself because we want to get at the end a really nice, smooth finish for the entire mold. So we're doing semi-finish and then we'll be doing finish. So as I said over here, we did a rest machining on those corners. And that actually are these corners over here. And then we've gone in and started to doing a finish cut. Now, in our linear finish cut that we've done here, you'll note that the tool is actually going to be working only on these surfaces over here when we take a look at our tool path. That's because that within my operation, what I've done over here is I've created a boundary manually in this particular case. And the boundary that I've created is only around this area and this area itself. In other words, those are the only areas where it's going to be machining. Now, my next finishing area will actually be this area itself. If we take a look at the tool path that was created here, you'll see that it's only working inside this area itself. What I've done in the next operation, again, I've done the rest machining operation to cover the corners of the areas that could not be machined. But this time I'm going down and doing it on a finish cut. If we take a look at the operations, all my finish cuts, my wall offset and floor offset are at 0. Now, if we take a little look at this area over here, we have on the part this area around over here and this area over here, which I really do need a small end mill to go in there, but I'd like to actually do it according to the shape of this area. So for that, we've used the option of constant step over in the part itself. If I were to go into my edit of this part, we use the option of 3D constant step over using a small 3mm ball end mill. And my drive boundaries was actually the boundary around each one of those areas. Now, I've done this actually in 2 steps, using a 3.3mm ball end mill, using passes of every 0.04 millimeters, and since this is a really small area, I've also continued on in another operation over here, using this same feature, but using a smaller end mill now, and using even a smaller side step. This way I'm basically guaranteeing myself that my part at the end of the day will really have a really nice smooth look to it and a clean finish that will not need any kind of hand finishing operation on it, such as polishing. Thank you for joining us on our demonstration for high-speed machining. Take care and have a nice day.